Hello, everyone. I'm very glad to chair this webinar. My name is Zheng Li. I'm from Queen's University. Today's speaker is Shuokang Huang, and his talk is on edge computing for radio frequency-based human sensing. Shuokang is a PhD student in Julie's group at Imperial College London. His research focuses on human sensing with Wi-Fi channel state information, device-free radio frequency sensing, and applied machine learning on RF sensing. And Shuokang's previous experiences involve semi-supervised adversarial learning, federated learning, etc. He received his master's degree and bachelor degree from Peking University and Sun Yat-sen University, respectively, in 2021 and 2018. In today's webinar, Shuokang will explore how edge computing and machine learning can enhance device-free radio frequency sensing in IoT systems. And he will delve into technical foundations, practical implementations, and emerging use cases that are shaping the future of human-centric edge AI systems. To be honest, the radio frequency sensing is out of my expertise, but I think the use case is very easy to understand and very promising, especially in the healthcare domain, based on my knowledge. And I believe Shuokang's work is directly related and very promising to the current, actually ongoing healthcare provisioning, from the hospital-based mode to the home-based mode. So I'm looking forward to learning more today. So Shuokang, the stage is yours. Please go ahead.
Yes, hi, good afternoon, everyone. I'm Shuokang, a final year PhD student at Imperial College London. So firstly, let me share my screen. Yes, can you see my screen here?
Yes.
Okay. So good afternoon. Welcome to this National Edge AI Hub webinar. The title of this webinar is Edge Computing for RF-based Human Sensing. Firstly, I would like to introduce the motivation of human sensing with RF signals. Human sensing is a collective term that covers the collection, processing, and analysis of signals to recognize human identities, locations, activities, and so on. It supports a lot of applications, such as security monitoring, smart homes, and healthcare. Most existing human sensing solutions rely on on-body sensors and cameras, but they have some limitations. For example, on-body sensors require users to wear devices and may intrude on human movements, which are intrusive. On the other hand, most cameras are relatively sensitive to environments, such as illumination and line of sight conditions. Recently, RF signals have been applied to tackle the limitations of on-body sensors and cameras, but most of them require dedicated devices, reducing cost effectiveness. Therefore, Wi-Fi-based human sensing has emerged. Because human movements inevitably interfere with Wi-Fi signals and lead to signal variations, we can extract human features from such variations. Specifically, such variations are recorded in Wi-Fi CSI. Because this solution does not require users to wear any devices, it has the advantage of non-intrusiveness. Wi-Fi signals can also work under low light or non-line of sight conditions, making it environment robust. More importantly, there are ubiquitous existing off-the-shelf Wi-Fi devices, making Wi-Fi-based human sensing relatively device-free. Despite these advantages, it is still very challenging to extract human features from Wi-Fi CSI because Wi-Fi was initially designed for wireless communication rather than human sensing. Because these human features are not observable for human eyes, and they are typically intertwined with excessive noise. Therefore, it motivates us to explore representation learning with Wi-Fi CSI to extract useful human features. Specifically, we focus on Wi-Fi-based identification, localization, activity recognition, pose estimation, and datasets. Although existing studies have made remarkable progress in Wi-Fi-based human sensing, there are still some practical challenges in representation learning with Wi-Fi CSI, and we aim to address these challenges. The first challenge is incomplete CSI samples. Due to the constraints of those edge Wi-Fi devices, most studies apply fixed windows to collect CSI samples, which may fail to match different activity durations. For example, when a person is walking but suddenly falls down, these fixed windows may only capture the signals of walking but not falling down. Device failure or human errors may also lead to missing values in CSI. These incomplete CSI samples undermine Wi-Fi-based representation learning, and our work aims to tackle this. The second challenge is multi-user activity sensing. Most existing studies focus on Wi-Fi-based single-user sensing, while multi-user activity sensing is more challenging because of increased user occlusion and mutual interference. Although researchers have begun to study Wi-Fi-based multi-user activity sensing, there is no public dataset and benchmark available for comparable and reproducible research before our work. Therefore, we aim to tackle this by constructing the first benchmark dataset. The third challenge is the scarcity of fine-grained neighbors. According to the experiments on our newly collected datasets, there is still vast room for improvements in Wi-Fi-based multi-user activity recognition. Specifically, when models learn human features from CSI for multi-user activity recognition, their representation learning is hampered by the scarcity of label data and the supervision of coarse labels. Therefore, our work aims to tackle this to further improve multi-user activity recognition based on Wi-Fi CSI. Finally, our work further discusses the challenge of cross-modal human sensing. For 3D human pose estimation, previous literature has only discussed single-domain learning, which is confined by domain-specific confounders and cannot generalize to new domains. Therefore, our work aims to tackle those subject-specific and environment-specific confounders to further improve cross-domain 3D human pose estimation. To address the first challenge, incomplete CSI samples, our work proposed temporal augmentation with diffusion models. The objective of this work is to tackle fixed windows by forecasting and handle missing values with imputation, after which we can recognize human activities with augmented Wi-Fi CSI samples. Specifically, we propose DIFF-AR, adaptive conditional diffusion model, where a diffusion model synthesizes augmented CSI samples and an ensemble classifier recognize human activities based on augmented CSI and raw CSI samples. Regarding the novelty of our work, existing conditional diffusion models synthesize samples through progressive steps guided by constant conditions, while different steps may actually require step-specific conditions to synthesize the patterns of different granularity. Therefore, we devise an adaptive conditioner to learn step-specific information for diffusion models, as shown in these formulations. Our work involves the training and synthesis of models. During the training of model, we regard raw CSI as augmented CSI and mask these CSI samples to simulate incomplete CSI samples, after which we apply the adaptive conditioner to extract step-specific information for the training of diffusion models. After the training of models, we directly take incomplete CSI samples as inputs for the synthesis of augmented CSI. To evaluate the performance of our proposed method, we adopt 4 public datasets for experiment. Firstly, we evaluate the quality of augmented CSI. Compare with state-of-the-art generative time series models. Experiments show that DiffAR achieves the best quality of augmented CSI in terms of MAE, MSE, and CRPS. Secondly, we evaluate the performance of human activity recognition compared with state-of-the-art Wi-Fi-based models. Experiments show that our proposed method outperforms state-of-the-art Wi-Fi-based human activity recognition methods. Overall, to the best of our knowledge, our work is the first to apply diffusion models to tackle incomplete CSI samples, achieving the best quality of augmented CSI and outperforming state-of-the-art methods in terms of human activity recognition. To tackle the challenge of multi-user activity sensing, we construct WiMANS, the first benchmark dataset for Wi-Fi-based multi-user activity sensing. For 11,286 samples in WiMANS, each 3-second sample includes 0 to 5 users performing activities simultaneously. The dataset collects the signals of dual Wi-Fi bands, along with synchronized videos for reference. All samples in WiMANS are annotated with user identities, locations, and activities. Specifically, we designed simultaneous scripts to instruct users to perform identical or different activities at varying locations independently yet simultaneously. We collect Wi-Fi CSI in 3 different environments, including a classroom, a meeting room, and an empty room. We evaluate Wi-Fi-based models in terms of identification, localization, and activity recognition. Benchmark experiments show that Wi-Fi-based models still have vast room for improvement compared to video-based models. We further discuss the performance of human sensing with respect to the number of users. As expected, sensing more users simultaneously results in lower performance. Finally, we compare the efficiency between Wi-Fi-based models and video-based models. As we can see in this table, Wi-Fi-based models show their superiority over video-based models in terms of model complexity and time efficiency. Overall, to the best of our knowledge, our work constructs WiMANS, the first benchmark dataset for Wi-Fi-based human identification, localization, and activity recognition. According to the results on WiMANS, there is still vast room for improvement in Wi-Fi-based multi-user activity recognition because of the scarcity of fine-grained neighbors. Therefore, we propose CORS-AR, cross-modal contrastive learning, to further improve multi-user activity sensing. CORS-AR applies self-supervised contrastive learning to leverage unlabeled CSI data and utilize auxiliary labels from pre-trained vision models as cross-modal supervision. Specifically, we apply intramodal contrast between unlabeled CSI samples and applied cross-modal contrast between unlabeled CSI and auxiliary labels, as shown in these figures and this algorithm. To further improve model efficiency, we devised the dual-stim dilated multi-layer perceptron as the backbone of our model. The proposed D2MLP model applies patch dividing and delayed resampling to avoid the use of complicated models. Specifically, two streams in our model learn temporal and channel-wise features respectively and aggregate features in a gating fashion. We evaluate our method on 3 datasets, including our newly collected dataset Wyman's. Experiments show that CORS-AR achieves the state-of-the-art multi-user activity recognition performance on our proposed datasets. We also compare models in terms of their efficiency, where our proposed method achieves better accuracy with relatively higher efficiency. Overall, to the best of our knowledge, this is the first attempt that addresses scarce label CSI data via contrastive learning and tackles course activity labels with cross-modal supervision. Finally, we discuss cross-modal human sensing. Specifically, domain-specific confounders cannot generalize to different domains and thus confine the performance of human sensing. It motivates us to study how to eliminate domain-specific confounders in RF signals and represents the signal variations caused by each individual human body parts for cross-domain human pose estimation. To this end, we propose GenHPE, generative counterfactuals, for cross-domain 3D human pose estimation. This method introduces skeleton manipulation to eliminate domain-specific confounders and uses an encoder-decoder model to learn domain-independent representations. We evaluate the proposed method in 3 different scenarios, including random split dataset and cross-subject or cross-environment scenarios. Experiments show that GenHPE significantly reduces estimation errors in cross-subject and cross-environment scenarios. We further evaluate the performance of GenHPE with or without generative counterfactuals, which indicates that generative counterfactuals indeed improve the performance of 3D human pose estimation in cross-subject and cross-environment scenarios. Overall, to the best of our knowledge, this is the first attempt using generative models to help RF-based models generalize across domains. In summary, our work focuses on edge computing for RF-based human sensing. Specifically, we study Wi-Fi-based human sensing, which is non-intrusive, environment robust, and device-free. We aim to propose novel models and datasets to address the practical challenges which undermine the representation learning with Wi-Fi CSI. We introduce novel temporal augmentation to tackle incomplete CSI samples. We construct Wyman's, the first benchmark dataset for multi-user activity sensing. We propose novel cross-modal contrastive learning to address the scarcity of fine-grained labels. We propose novel generative counterfactuals for cross-domain 3D human pose estimation. We believe that our work can push the boundary of current research and open up new opportunities for edge computing in terms of RF-based human sensing. This is all of my presentation. Thank you.